All right, hey, how's it going? Are we live? Hello? Is this thing on? It's Magister Bourgeois again, doing the thing again. This time we're going to be reviewing. I appreciate the feedback I've been getting from you guys very much. Gives me some direction for how to do the review video for today. So let's get into it. So before I get into just straight up memorizing the formulas, if you are like a boss memorizer, go ahead and memorize the formulas for everything, because they are on that page 169, right? I prefer to conceptualize everything. So I want to start with prisms and cylinders. So let's take a look. Hopefully you can remember that the generic formula is volume. So this is volume now, how much three-dimensional space we're taking up. Volume equals the base times the height. Now the trick is always the base, because the base is going to be a two-dimensional figure, right? So let's take a look at some of the things here. So if the volume equals the base times the height, you look at a cylinder. The cylinder has a base that is a circle, and a cylinder, we have to assume that the top and the bottom are the same. So the cylinder has circles. We need to know the area of the circle in order to calculate the volume of a cylinder. A triangular prism, we need to know how to calculate the area of a triangle in order to calculate the volume of the prism. So in this case, this base, I highlighted it in yellow to kind of show we have a two-dimensional circle, a two-dimensional triangle, and a two-dimensional rectangle for prisms and a cylinder. A cylinder is very much like a prism in that respect. And then the height is going to be, they call it height. If you're laying on its side, it looks more like length. But I show what that is right there. So hopefully this visually can help you. Now, so this is the generic formula to calculate the volume for any figure that's like this, where we have a base that is, let me do that. A base that is a two-dimensional shape and it's at two different ends. So there's two ends with the base, and then between those two ends is just a bunch of length. It's just a whole bunch of solid. So this is the generic formula that you can use for this, this, and this. But how do we calculate this B? The B is the part that changes. So for our circle, the B is the area of the circle is pi times the radius squared. Pi times the radius squared gives us the B for the circle. Let me highlight that yellow. There we go. The B for the triangle, these are two-dimensional shapes. This should be review. Actually, let me do the rectangle first. So length and width. So this B equals length times width. You just multiply the two dimensions, right? Think about what would happen if we cut a rectangle in half. What are we left with? Let's suppose that those are two equal halves. I didn't draw the line perfectly. It's really hard to do. But if we cut it in half, then what's the area of 1/2? Well, it would be 1/2 of the length times the width. And what we just did here was we found the area of the triangle, right? So the triangle, its area is 1/2. They call this the base times the height, but it's basically the same thing. It's 1/2 of 1/2 of the dimensions, where if you put two of these triangles together, you would basically have some kind of a rectangular thing. So does that make sense? So 1/2 the base times the height, and the height is, what would it look like if you made a right angle here. So if we were going to use this line as the base, if I flip my triangle over, then it would be this base times this height. Or if I was using this side, it would be this base times this height. It doesn't matter which one you use as your base and which one as your height. It really doesn't matter, because all that matters is it'll always work out to this. So pick one side as your base, and then draw a straight line up to the corner farthest away from that base, and that's your height. And then take half of it, because if you just do the base times the height, you're basically doing a rectangle. We don't want a rectangle, we want half of a rectangle, also known as a triangle. Well, half a rectangle if you can bisect it from vertex to vertex. Does that make sense? That's how I've always remembered the area of a triangle. It's like 2 halves of a rectangle slash a square slash a rhombus, whatever. The point is, it works. The system really works. Okay, so once we have the base, we multiply it by how far apart the 2 bases are. And that tells us how much space it's taking, how much space our prism or cylinder is taking up. Now, what about surface area? This gets a little bit more tricky, but let's start with the easy ones. The surface area for, let's do the rectangular prism. I think that's the easiest one. We have the area. How many sides do we have? We've got 1, 2, we've got the bases. And then if we talk about the height has 4 sides. 3, 4, 5, 6, right? We have 4 sides plus the bases. So 1, 2 bases plus 1, 2, 3, 4 sides. That's 6 total faces of this prism. So the faces, each face is a rectangle. So basically we're just going to take this formula right here, length times width. Let me erase that 1/2, because that's, I said erase. Erase that 1/2, because that's what I was doing to illustrate the triangle. We're going to take this length times width. We have the length times the width right here. We have the length times the width right here. We have the area of those 2 rectangles that are highlighted in yellow. And then we're going to have the length times the width of the heights, the height, length, and width 4 times. And you'll see some of these edges on this prism. If you want to get, like, I don't know, a cereal box or something to kind of show, to kind of see a 3-dimensional piece, you'll see that any edge is shared between 2 of its faces. All of the edges are borders between 2 faces, and so yeah, some of those dimensions are going to be the same, but each face is a rectangle. You calculate the length times the width, you add all of them up, add every face together, that's your surface area. Over here, the surface area of this prism is going to be the triangle, and then this triangle, and then this is a rectangle. We have 3 rectangles instead of 4 rectangles like this prism. So we only have 3 rectangles. Triangular prisms really aren't super common. I mean, sometimes, like, if you go to the UPS store and say, hey, I want to ship a poster, they'll hand you a triangle thing, or else they'll hand you a cylinder thing like this. But I've mostly seen them in triangles, because triangles are easier to flatten out, and it's just an easier shape to deal with than a cylinder. It won't roll away when you set it down. Then you have the cylinder. The cylinder is a tricky part. I'm cheating right now. I'm looking on page 169. So the cylinder, we still have the area of a circle. That's part of it. We have the area of another circle. That's another part of it. So we have 3 faces. Let me make notes here. So over here we have 6 rectangle faces. Cursive is just easier with a touch screen. Over here, we have 2 triangles, and we have 3 rectangles. We have to calculate those. Also, one caveat, these rectangles, there can be 3 different shapes of rectangles over here. You could have the base, you could have this what I drew as long. It doesn't necessarily have to be long. So this base, or you could call these the bases, or you can call the top and the bottom right now the bases. The bases are kind of tricky, because however I position my shoebox, defines which one is the base, right? Which one's the bottom, which one's the top. It depends how you're holding it. Over here, we're looking at two circles, and then we have one, I don't even know, one loopy thing, one curled up tube. They called it the curved surface in the book. You can call it that if you want. I think we should keep that terminology consistent. The curved surface. It's the tube. The curved surface of a cylinder. So we have the formula for a rectangle, the formula for a triangle, 1/2 base times height. We have the formula for a circle, which is, pi r squared, right? So now we're looking for, we need the surface area of a tube, and they give that on page 169. If this is new to you, it should be. I reckon it is. You're going to need to straight up just remember it. It's 2 times pi times r times h. And h in this case is how long the tube is. The radius is how wide the tube is. The h is how long the tube is. So those are the two unknowns that they would need to give us, right? Remember, the radius is halfway, is 1/2 of the diameter. The radius is 1/2 of the diameter. It's from the exact middle all the way to the edge of a circle. Capiche? All right, so that takes care of the surface area of these three shapes. Remember, surface area is it's a two-dimensional measure, so it's going to be square centimeters, square inches. It's also how much, you can think of it as how much paper it would take to make an origami version of this, or how much paint it would take to paint one of those. Like how much two-dimensional space the paint would take up if it was laid out flat. Next, I'm going to slide down. So let's look at a cone. Cone is the next one on the doohickey. I somewhat lament that we didn't have the resources and time and ability to do some of the hands-on activities together. Really? Really, whiteboard? You're going to be like that? All right, fine. But so let's start with a cylinder. I want everybody to imagine with me. We're going to use our imaginations. You have a chunk of clay, and that chunk of clay is right now in the shape of a cylinder. And that chunk of clay is on a scale, and that scale says, oh, let's say pounds, because we're American, why not? It's 3 pounds. You have a 3-pound chunk of a cylinder clay. Over here, you have another chunk of clay that is shaped like a perfectly shaped block. It's like just a straight up rectangular prism block, and it also weighs 3 pounds. All right, 3 pounds of clay here, 3 pounds of clay there. Now, what you start doing is you say, I don't want a rectangular prism and a cylinder anymore. I want a cone and a pyramid. And so what you start doing, let's do the pyramid first because I feel like that's easier. You find the exact midpoint of this square, and you start shaving. You take your hot little wire and you start shaving off the sides, shaving away clay from this middle of the top all the way down to the corners, and you shape it. You make a pyramid. I should have done that in a different color. Let's do that over again. So you make this tall, skinny pyramid, and what you do is you take all that clay and you tear it away. Now, I want you to make a guess. You might already know the answer to this. How much? So the four sides of the base are still intact. The vertex is right right at the top where it always was. So you have a perfect pyramid with a square base. You draw those invisible edges that you can't see. It has a square base, and so there are 4 triangular sides going around and a square base on the bottom. What do you think the scale shows right now? You peeled away some of that clay. Make a guess. What does your scale show now? Pause the video and tell me what you think. All right. The correct answer would be, assuming you made a perfectly dimensioned pyramid, your 3 pounds of clay became 1 pound of clay. So if the height is the same and the base is the same as your prism, you tore away 2/3 of its clay. 2/3 of its volume is now gone. And so now you have 1/3 of the clay still sitting on the scale. So we took the volume formula, where the volume of the rectangular prism was the base times the height. The volume of your pyramid is 1/3 of that. Did you see that? It's the same as a rectangular prism, but it's 1/3. 1/3 the base times the height. For any pyramid. This also works for a triangular pyramid, a pyramid with a triangular base. It's the same. You take the triangular prism, you cut away 2/3 of it, and you're left with 1/3 of the base times the height as the volume. Now, hopefully you can guess where I'm going with the cylinder. It works the exact same way. The cylinder, the volume is going to be, if you carve this away, let me try that again. You carve away 2/3 of it, and it's still got a round bottom, but now it's you took away 2/3 of the clay. So your newly formed shape is only 1 pound. So once again, this formula is the same for a cone or a pyramid. It's 1/3 the base times the height. It works. The hands-on activity had you fold up some paper and make a cone, and then fold up some more paper with a cylinder, and then you scoop up some rice into the cone and pour it into the cylinder. You do that 3 times before the cylinder fills up, because the cone holds 1/3 as much rice as your cylinder, even though they have the same height and the same base. Pretty nifty. I think it's pretty cool. All right, so that's the volume of these two things. Looking at the surface area. Once again, the surface area for the triangular prism, you can just mentally see still that the this is made up of 2-dimensional shapes, right? So the base on this one is a triangle, the base on this one is a square. So we have the area of this square, length times width, plus this triangle, 1/2 length times width, but that triangle is multiplied by 4. I have 4 of that triangle. You see? Now in your book on page 169, I have no idea what that little lowercase s stands for right now. Oh, that's the slant height S. Why are they using S here instead of that swirly thing that they were using just a second ago? Whatever. They simplified the formula. So in your book, it says S equals, the surface area equals the base plus 1/2 P and lowercase s, where they say P is the perimeter of the base. They're doing the same, they're basically doing the same thing. It just simplifies out that way. So you have one triangle plus another triangle plus another long triangle plus another long triangle. So you have 4 triangles. I mean, I could work it out, but just trust me, the math works out the same. You have 4 triangles. I'm going to work it out, I guess. 4 triangles. So 4 times 1/2 Let's say this is a square, and so the perimeter is 1. That's an ugly one. 1. There we go. So each side is 1. I don't know, inch. 1 inch long. So 1/2 times 1 times the height. If this is 1, let's say the height is, and we're looking at the slant height. Slant height. We need that slant height because if we just go straight up with the height of the pyramid, it won't be the same as the height of this flat two-dimensional triangle that we're looking at. So let's say the slant height is 5. Why not? So actually, let's make it 6 because then we're dealing with even numbers. So 6 times 1 is 6 times 1/2 is 3. So the area of this long flat triangle is 3 square inches. 4 of those is 12 square inches. Now let's plug it into the equation as they give it to us. So they say S is the perimeter. The perimeter is 1, 2, 3, 4, and the slant height is 6. So 4 times 6 is 24, times 1/2 is, 12. It comes out to the same number because I said so. It's magic. So if you only remember that your surface area is the area of each two-dimensional face of the thing that you're working with, that'll be good enough to get you through to calculate any surface area of this thing. Now then, a cone. The cone, you have the area of the circle. What's that again? Raise your hand. Bingo, good job, Cam. It's pi r squared. You got it. Pi r squared. So we got the circle plus the swirly part. My rainbow pen's been on the blue-purple side of things for a long time. I only know that because it's obviously a cool color, not a warm color like red, orange, yellow. So the curly part, this is where it gets wonky. I think you just have to memorize this formula. I have no fun way to doodle this out. But it's pi times the radius times the slant height, which is this length right here. The height, slant height. Not to be confused with Fahrenheit. Just memorize it. I got nothing. Spheres, you guys. Spheres, straight up just memorize. I got nothing for this either. The interesting thing is we still, just like the pyramid and the cone, we have a third involved, which I wonder why that is. So we have the sphere, they do a little doodly-doo, they do the little belts around it to show you, hey, it's in 3 dimensions. The radius is the middle of the sphere to any point on the surface is the radius. And once again, we have a third involved, but this time it's 4 thirds times pi times the radius cubed. Because we're dealing with 3 dimensions, we cube the radius. That's the volume. Memorizationalize it. The surface area, it's like 4 circles. So the circle is pi r squared. A sphere is like 4 of those. 4 pi r squared. So if it helps to remember that there's a 4 in the surface area and in the volume, I mean, anytime you're dealing with something round, pi has to be there. Pi helps us get around. So any formula, if you're writing down your formula and it's something round and you don't see pi in it, you're wrong, because it needs pi. Pi is the going around number. Also, it's going to need the radius because the radius pretty much tells us how big the circle is, how big the roundness is. Okay? Check mark. That took a little bit longer than I wanted it to. However, I think it was useful. I had fun. I hope you did too. I know at least half of you did. So, I want to talk about composite solids. Someone asked about composite solids, and when we're looking at composite solids, we need to kind of really try to visualize things out. So any composite solid is going to be a shape that can be described in terms of two different shapes together, right? So like I could take a cone and plug it on top of a sphere. Let's do that. Let's say that I have a cone. I'll make it a wide cone. Dot, 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 dot. And I want my radius to be, let's say 3 units is my radius. And then I have a sphere. And my sphere also has a radius of 3 units. And I want to take this cone, and I want to put it on top of this radius, and I want to stick it on top of this sphere. Do you think you'd be able to tell me the surface area? Let's say I glue it on there real good. Do you think you'd be able to tell me the surface area of this composite? I think you should be able to, because you know the surface area of a cone. So obviously this cone has an open bottom, right? It's like an ice cream cone or a dunce cap. So if I wedge this cone really good and I glue it down tight on this sphere, we know that I've got the surface area of this curved surface, which is pi r slant height, I believe. Double checking. Yes, pi times r times slant height. So I'll need to give you that information. We got the cone, and we also have exactly 1/2 of the sphere, right? So that the sphere surface area it's 4 circles is the surface area of the sphere, pi r squared. However, we're only the top half is covered up by my cone. So my new shape that I have, which is like a, I don't know, a comet, whatever you want to call this composite shape that I've dreamed up, it's not a whole sphere. Only the bottom half of the sphere is sticking out. So if I wanted to paint this thing green, woohoo! How much surface area am I taking up of paint? So it's not a whole sphere, it's half of a sphere. So I multiply my sphere by 1/2. So the surface area of the sphere is going to be 2 pi r squared. The surface area of the cone, it doesn't have a base because the base is taken up by the sphere and it's a hollow cone anyway. So the surface area is going to be the slant height. So I'm going to add that, I have the sphere plus the cone, which would be pi r times slant height. So those two pieces added together would be my surface area of the whole thing. And then you say, oh, haha, well, what's the volume? Well, the volume is just going to be a cone plus half of a sphere, and that's the volume of the entire figure that I just made. Sometimes you might get a problem with a composite that is not two things added together, but something cut in half. I remember we did that birdhouse problem, right? Y'all remember the birdhouse, where there was a cube. There was a cube, but it had a pyramid on top, and then it had a hole cut out of it. And so we had to figure out the surface area, but we had to subtract a circle from it. Or what about if I could say, oh, I'm making a snowman, and it's got a cone for a nose, and it's got a couple of spheres for eyes that are stuck halfway down, and then I take a cylinder and I carve it out for the mouth. So you should, even though the cylinder is bent to make a smile shape, you should be able to figure out, okay, so I have the volume of a sphere plus the volume of a hemisphere here and a hemisphere here plus the volume of a cone here plus actually minus the cylinder scoop that I took out of there. So it's just each piece plus and minus away, plus, 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 minus. Add all those doohickeys together and you got your weird sculpture that you made. I realize that that's maybe not the most extremely helpful run through of how to think about composite solids, but it takes a little bit of creative thinking to you really have to visualize what's going on and figure out how's this? Anytime you're thinking of surface area, think about what is exposed to the air. Or yeah, if I spray paint this thing, what will my paint actually touch? If I go all around the whole thing with spray paint, what will my spray paint touch? Or if I wanted to, yeah, I mean, any way that you can think of how much space is being occupied in 3 dimensions, or how much the just what's touching air, just the outside part, how much that is taking up. I guess it doesn't work if you're talking about like a hollow cone, because then you'd be tempted to measure the inside and the outside. We're really just looking at the outside. Make sense? Anytime there's a problem involving a cup, the cup has a base on the bottom, but not on the top. Don't try to add that to your surface area because it's not closed on the top. If it's a tin can full of creamed corn, then yeah, you count the top. But if it's a cup or a glass, you're not going to add that circle. So you're going to have the surface area of 1 circle, not 2. So that's probably why one of the ways when page 169 is going to be less than helpful. 169 is not going to be helpful when you have to think more creatively about composite solids, or about things that have that are open on one end, or things that are, you know, when you're dealing with like the curved surfaces of a cylinder or a cone, stuff like that. The more I look at this guy, the more I'm starting to fall in love with him. Let's give him rainbow hair. I feel like we should name him. I love him. Okay, I was also asked if I could do number 9 and 11 from the from 8.4, and I think I had another student tell me that they disagreed with number 9. So let's settle this once and for all. Mr. Bourgeois is the final authority on what is true, at least as far as whether or not number 9 gives you the correct answer or not. Let's do it. So hey, you are dismissed. If you don't want to see practice problems 9 and 11 from lesson 8.4, if you don't want to see those, you are dismissed. Have a nice day. Thanks for watching. If you want to see them done, here they're about to get did. I'm gonna wait before you go. You already left. That's all right. I'll tell you anyway, in case you didn't already leave. I'm gonna upload practice checkpoints, or upload a practice version of the checkpoint. You're gonna do it. It's gonna be great, and I'm gonna go over that video. I'll just do all the problems on my next video. Sound good? I think so too. Okay, number 9, a solid metal ball with a radius of 10 inches, that is a very large metal ball, is melted and made into smaller spherical metal balls with a radius of 2 inches each. How many smaller spherical balls can be made? Okay, so we got a big hunk of metal. So practice problems 9, 11, page 162. Doop. There we go. So we got a big hunk of metal. How much metal do we have? I don't know. We got to calculate it. So 10-inch radius. We're going to plug in our the radius is 10, not the diameter. We're going to plug in our formula. So the formula is 4/3. We're finding our volume. This is how much metal do we have in this entire ball. 4/3 times pi times r cubed. I believe that's the formula from memory. Let me double check. Yeah, 4/3 pi r cubed. Okay, I'm going to use 3.14 to approximate. So 10 cubed is 1,000. 4/3 of that, I'm going to bring up my calculamatron, is, 133.33333. So let's see, do I want to keep pi? Yeah, we'll multiply it out. We'll just use really rough numbers. I'll keep the decimals going. We won't save pi. So times 3.14, we get 4,186.7. It's 2/3, but we'll round up to 7. So this is how much volume of metal we have. It says it's made into tinier balls with a radius of 2, right? So our tiny balls, radius of 2, let's calculate that. 4/3 times pi, 2 cubed, so 2 times 2 is 4, times 2 is 8, so we're dealing with 8 times 4/3 pi. Punch in the calculator, 8 times 4 is 32, divided by 3 is nearly 11, times 3.14, we get 33.49. So I'm gonna approximate this. I'm gonna round. Should I round? I don't know. Let's see. If I use my memory function, so I save this entire fraction thing into my memory. Then I'll go. Let's see. So I take 4,186.6666666 divided by memory we call equals exactly 125. So some of you have done rounding. I know some of the students rounded, and when you round the little ball volume and round the big ball volume, you'll get something like, oh, 125 point something, and you say I can only make, or you get 124 point something, and you can't round up to a whole ball. You can only round to, you can't round. However, if we were to leave this in fractions, we would see that it does divide perfectly evenly into 125, exactly 125 balls. It does assume that there's no waste, and we all know that anytime you are dealing in manufacturing, there's going to be like some drips of molten metal that don't quite get into the little spheres. So we're probably 124 balls would be an acceptable answer. I understand that rounding can lead to different answers. So here's what I did. The volume of my big ball, the volume of my little ball, I divided this volume by the little volume to figure out little volume. Little volume was, what was the little volume? 33.49. So about, my little volume was about 33.49 centimeters cubed, cubic centimeters of metal. No, inches. Beg pardon. Inches. We're in America. Cubic inches. So cubic inches. So I took the big volume, the volume of the giant sphere, divided it by the volume of the little sphere to figure out how many little spheres fit inside the big sphere. That's how many spheres I can make. Number 11. Let's erasify this. Take a snapshot. Too late, it's gone. 11Z's says the volume of a sphere is that many. What's the radius of the sphere? Okay, we're working backwards. So volume equals 4/3 pi r cubed. They give us the volume and they want us to find the radius. So the volume is 3,052.08 equals 4/3 times pi times r cubed. Okay, I remember, so this one, I can see where this one would start to get tricky. Let's simplify this and get the radius all by itself with algebra. So I want to get rid of the 4/3. Well, let's get rid of the pi. We're going to divide both sides by pi. So 3,052.08 divided by 3.14, we're going to approximate, equals 972. So 972 equals 4/3 times the radius cubed. I divided both sides by pi. Now I'm going to divide by 4/3. Guys, how do I divide by 4/3? I can divide by 4/3, but dividing by 4/3 is the same as multiplying by 3/4. Dividing by a number is the same as multiplying by its reciprocal. So I'm going to multiply both sides by 3 and then divide both sides by 4. So I multiply both sides by 3. I get 2,916. And then if I divide that by 4, I get 729. 729 equals the radius cubed. Now what do I want to do? I want to take this, let's use a different color, why not? I want to take the cube root of both sides. If I do the same thing to both sides, I'll be sitting square. So the cube root of both sides, how do I take it to the cube root? On my calculator, I'm going to do, if you have a cube root button, it will look like, it'll be like either second function. Learn how to do this. If you don't know how to do this on your calculator, do it before the checkpoint comes up. But you might push the second function. That's supposed to be second. And then x cubed. Because that second function would be, instead of cubed, it'll be cube root. It'll usually be in a different color on your calculator. Otherwise, you might push, you can always, any calculator, you can do it this way. I'll show the way that will work on 100% of your calculators. You type the number, you're going to type 729, and you're going to either do the caret feature to raise to the power of 1/3, or it's going to be a button that looks like this, x to the y, and then you can do parentheses 1 divided by 3, close parentheses, equals. Basically, you're going to raise it to the power of 1/3. However your calculator raises something to a power, raise it to the power of 1/3. You can take 1 divided by 3 equals, and you get 0.33333333. You can store that in memory, and then say raise to the power of, recall memory, and bring the memory up. Or you can just raise it to the power of, and then type 0.33333333 equals, and you'll be really doggone close. So that should work. So after we take the cube root of 729, we find that 9 is the cube root of 729. So 9 equals the radius, because 9 times 9 times 9 equals 729. So our radius is 9. So B, what is the surface area of the sphere? We're just going to plug those in. Do I want to do that or not? Surface area of the sphere. We'll do it, I guess. So B is the surface area of the sphere. Now that we know that the radius is 9, we should be able to figure out the radius of the sphere. Radius equals, or surface area equals 4 circles. So pi r squared times 4. I'm going to double check my formula. Surface area equals 4 pi r squared. That is true. So the area of a circle is pi r squared. The surface area of a sphere is 4 of those, 4 circles. The r is 9. 9 squared is 81. 81 times 4 times pi. I'm going to plug that into my calculator. 81 times 4 times 3.14 equals, come on now, equals 1017.4. That's my final answer, and that's meters squared. All right. Love, joy, and peace, you guys. Catch you later.